Hello dear students, welcome to mathematics class. In this class, let us discuss linear equations which are reducible to homogeneous form. So up to the previous video, we have discussed the linear equation which are in homogeneous form. So the standard equation or the standard form of the homogeneous form is here, that will be x power n d power n y by dx power n, then a1 x power n minus 1 d power n minus 1 y by dx power n minus 1, and so on. A and y is equal to f of x. But here it is not in that form, because here we have a naught and instead of x we have a linear equation, that is a plus bx whole power n d power n y by dx power n, and then a1 a plus bx. Here also we should have the same equation, that is a plus bx whole power n minus 1 d power n minus 1 y by dx power n minus 1, and so on up to a n minus 1 a plus bx dy by dx plus a n y is equal to f of x, where a naught a1 so on up to a n a b, they are all constants. So this is the standard form of the that linear equation, that is non-linear equation, because it is not in homogeneous form. So now we are reducing that to the homogeneous form. So in the previous case we have substituted x equal to e power z, but here the only difference is we need to substitute a plus bx equal to e power z, then z becomes log of a plus bx. Then here differentiating this one, we will get dz by dx equal to b divided by a plus bx, because differentiation of log x is 1 by x, right? That is 1 divided by a plus bx, and again we need to differentiate a plus bx with respect to x, that is equal to b. Then dy by dx, now this can be written as dy by dz and dz by dx, because we have expressed x in terms of z. So therefore first we need to differentiate y with respect to z, then z with respect to x, and we know that dz by dx equal to b divided by a plus bx, which is into dy by dz. So therefore dy by dx equal to what? A b divided by a plus bx dy divided by dz. So now on cross multiplying we get a plus bx into dy by dx equal to b into dy by dz. So just send or just shift this a plus bx to LHS. So that becomes of the form a plus bx dy by dx equal to b into dy by dz, and consider that as the second equation, and the given equation is first one. Then again for the second order derivative, so here we have dy by dx, then differentiate that once with respect to x, we will get the d square y by dx square equal to d by dx of dy by dx, and we know that dy by dx equal to b divided by a plus bx into dy by dz. So here it is the product of two functions, so hence we need to apply the product rule to differentiate this term. So now second function dy by dz as it is, and differentiation of this one. So we know that differentiation of 1 by x equal to d by dx of 1 by x, that is minus 1 by x square. So therefore here minus 1 divided by a plus bx whole square, and differentiation of a plus bx is b, so already 1b is there, that becomes b square dy by dz plus. Now dy by dz we need to differentiate, so the first function as it is, dy by dz equal to d square y by dz square, and again differentiate z with respect to x, that becomes dz by dx. And now here b square a plus bx whole square dy by dz plus b divided by a plus bx and d square y by dz square as it is. Now substitute dz by dx, that is b divided by a plus bx, because here already we have dz by dx equal to b divided by a plus bx. So therefore here we have substituted that dz by dx. Then simplifying this one, so the first term will be as it is. So here b divided by a plus bx into b divided by a plus bx, that is b by a plus bx whole square. Now again cross multiplying, here we have a plus bx whole square, here also we have a plus bx whole square. So therefore we can shift that to LHS. Now the equation becomes a plus bx whole square into d square y by dz square is equal to this minus b square into dy by dz plus here remaining b square d square y by dz square. Now b square is common, remaining d square y by dz square minus dy by dz, and consider this as equation number 3. Now put d by dz is equal to capital D. In the previous case we have considered x into d by dx, right, that is equal to capital D, that is nothing but d by dz only in the or while solving the linear differential equation of homogeneous form, which are in homogeneous form. For that we have considered d by dz is a capital D. So here also same, d by dz equal to capital D. Then from equation 2, so here this is the second equation. Now a plus bx into dy by dx, right, is equal to d by dz equal to what, capital D. Then it becomes here a plus bx dy by dx as it is, then b into dy, because capital D is d divided by dz, right. Then from equation 3, so here we have equation 3, that a plus bx whole square d square by dz square equal to this one. Now here so here it is equal to d square y by dx square, not z square. So d square y by dx square equal to this b square into d square y by dz square minus dy by dz. Then here a plus bx whole square into d square y by dx square is equal to this b square as it is. Then d square y by dz square, that is the second order derivative, so that becomes d square y minus dy. Now by taking d and y common, so if you take d common, remaining d into d minus 1, so y is also common, so therefore d into d minus 1 into y. Then similarly for the third order derivative, that is a plus bx whole cube d cube y by dx cube is equal to, here we have b square, now we will get b cube d into d minus 1 into d minus 2 y, and so on. A plus bx whole power n into d power n y by dx power n equal to b power n d into d minus 1 d minus 2 and so on d minus of n minus 1 into y. So this procedure is similar to the previous case. There we have considered x into d by dx equal to capital D, then x square into d square by dx square equal to d into d minus 1, x cube d cube y by dx cube equal to d into d minus 1 into d minus 2. Here also it is same, but the only extra thing is here we are considering b, b square, b cube, b power 4 depending on the order of the derivative. So here b is coefficient of x, that should be the coefficient of x in the given differential equation. So now it is in general, that is a plus bx whole power n into d power n y by dx power n. Then substituting all those terms in equation 1. So here we have equation 1, that is a naught a plus bx whole power n into d power ny by dx power n. So now we know the value for this expression. So therefore that is a naught b power n d minus 1 and so on up to d minus of n minus 1. And for the next one, the power is n minus 1. So therefore a1 as it is, then b power n minus 1 into d minus 1 and so on d minus of n minus 2 and so on up to the last term here an minus 1. So here its power is 1, so therefore it is b, and here dy by dx, so that becomes capital D plus an into y is equal to f of. So by substitution z equal to what? Log of a plus bx, right, or a plus bx equal to z. Then from this substitution we can write x equal to what? E power z minus a divided by b. So therefore here we have f of x. So instead of x we need to substitute the new variable, that is e power z minus a divided by b, which is a linear equation with constant coefficients, and hence it is solvable for y in terms of z. Let the solution be y equal to capital F of z. So once we got the solution in terms of z, then we need to replace z equal to log of a plus bx. Hence the required solution is y equal to f of log of a plus bx, which is the required solution for the given differential equation. So remember, here we need to substitute a plus bx equal to z, so a plus bx equal to e power z, or z equal to log of a plus bx, and a plus bx into dy by dx equal to what? B into d, and a plus bx whole square d square by dx square equal to b square into d minus 1. There we have substituted already d into d minus 1, d into d minus 1 into d minus 2 and so on. But here the only extra thing is that b, where b is the coefficient of x in the linear equation a plus bx. So let us consider one example on this reducible to linear differential equation in homogeneous form. So here the equation is 5 plus 2x whole square d square by dx square minus 6 into 5 plus 2x dy by dx plus 8y is equal to 0. So here the RHS is 0. Whenever the RHS is 0, then it understood that the complementary function itself is the complete solution for the given differential equation. So to solve this equation, first we need to substitute that the linear equation. Here the linear equation is 5 plus 2x, right. So therefore first put 5 plus 2x is equal to e power z, or z equal to log of 5 plus 2x, and next is that is d by dz equal to capital D, right. So it means that a plus bx whole square d square by dx square equal to what? B square into d minus 1 into d minus 2, and a plus bx dy by dx equal to b into d, right. So now let us make the substitutions here. Now this equation becomes, so here 5 plus 2x whole square d square y by dx square, right. So now here we have a plus bx whole square d square by dx square is equal to what? B square into d minus 1 y, right. So here b is equal to what? B equal to 2, because the coefficient of x in the linear equation, that is only b. So then this becomes 2 square d into d minus 1, which is equal to 4, here y will come, so 4 into d square minus d into y. On simplifying this, we get 4d square minus 4d into y, right. And next consider 5 plus 2x into dy by dx, 5 plus 2x dy by dx. So here it is a plus bx dy by dx, here a plus bx dy by dx equal to b into dy and b equal to 2 in this case. So therefore this becomes 2 into dy. So only these are the substitutions. Now consider this as equation number 1. So therefore equation 1 becomes here 5 plus 2x whole square d square y by dx square is equal to this one, that is 4d square minus 4d into y minus here 6 as it is, then here it is 2 into dy plus 8y is equal to 0. Now take that y common from each term, then it is 4d square minus 4d minus x into 2, that is 12d plus 8 into y equal to 0. Then here 4d square minus this becomes 16d plus 8 into y equal to 0. So now here we can consider that 4 common, right. Then 4 into d square minus 4d plus 2 into y equal to 0, or it implies that d square minus 4d plus 2 into y equal to 0. Now this equation looks like linear differential equation with the constant coefficients. So once we got this equation, then it is very easy to solve. So considering the auxiliary equation and finding the roots and then writing the corresponding complementary function. So here the auxiliary equation is m square minus 4m plus 2 is equal to 0. Then here now roots of this equation, so it is the quadratic equation in m. Then so by applying the formula that m equal to minus b, that becomes 4 plus or minus square root of b square minus 4ac, b square is 16 minus 4 into 2, c equal to 2 and a is equal to 1 divided by 2, which is equal to 4 plus or minus 16 minus 8, that is 8, and root 8 can be written as 2 root 2 divided by 2, which is equal to 2 plus or minus root 2. It implies that 2 plus root 2 and 2 minus root 2 are the roots for this equation. So now here for writing the complementary function, the conditions are same. So here these two are real and distinct real roots. So therefore whenever the roots are real, then the complementary function will be c1 e power m1x plus c2 e power m2x. But here instead of x we need to consider z, as in the previous case we have considered z. So therefore here we need to consider z in terms of, in place of x. So therefore y is equal to c1 e power, the first root is 2 plus root 2 z plus c2 e power 2 minus root 2 z. So here we are writing y, not cf. We are writing y because here on RHS we have 0. Whenever 0 is there, then the complementary function will be the complete solution. So therefore y equal to this one. Then y is equal to c1 e power z equal to what? 5 plus 2x. So therefore 5 plus 2x whole power 2 plus root 2 plus c2 into 5 plus 2x whole power 2 minus root 2 is the required complete solution for the given differential equation. So here just substitute a plus bx equal to e power z, that is the main thing. Then go on substituting corresponding to the terms in the given differential equation. So if it is a plus bx whole square d square by dx square, that is equal to b square into d minus 1. If it is 3, then d cube y by dx cube, then that will become b cube into d minus 1, d minus 2 and so on. So already we have discussed the previous examples, that is linear differential equations which are in homogeneous form. So there we have substituted x equal to e power z, and here a plus bx equal to e power z, that is the only difference. And while writing the complementary function, instead of x we need to use z, then afterwards e power z can be replaced by the corresponding substitution.